Off-grid plant. Tools and equipments required. Block diagram of 1 kilowatt solar PCU. Ready to use individual blocks. 4 multiplied by 250 watt solar panels mounted, wired and assembled through combiner box suitable for charge controller. Charge controller 24 volts, 40 amperes suitable for inverter. 1 kilowatt solar inverter with suitable solar DC input and battery bank input terminals. Battery bank 4 multiplied by 12 volts 100 ampere hour connected suitable for given inverter. DC disconnects, AC disconnects, tools and accessories. Wiring diagram, wired blocks and interconnected. Study the block diagram of off-grid solar photovoltaic electrical system. The block diagram of solar photovoltaic electrical system contains several blocks and some of them are given below. Solar photovoltaic array. The photovoltaic solar panels are made up of individual photovoltaic cells connected together and it is called as a solar photovoltaic. Array junction box or combiner. AJB, also referred to as PV combiner boxes. It connects DC power from PV strings with blocking diode on each string for protecting panels from reverse current flow. The collected power is then transferred to charge controller. Charge controller. A charge controller, charge reflector or battery regulator limits the rate at which the electric current is added to or run from electric batteries to protect against electrical overload, overcharging and overvoltage. Battery bank. A solar battery bank is a device that can be added to SP system to store electric energy generated by from solar panels. The group of batteries connected in different combinations to required output voltage levels. Solar inverter. A solar inverter is a device that converts the DC direct current from solar panels into AC current which is used by domestic and commercial appliances. AC loads. In this block, receiving the AC power from inverter block and distribute the different AC loads of domestic and commercial appliances. Observe the energy flow paths and type of energy. Energy flow paths. Energy flow path 1. Solar photovoltaic array. Input sunlight. Solar panels are usually made from silicon or other semiconductor material installed in a metal panel frame with a glass casing. When this material is exposed to photons of sunlight, it releases electrons and produces an electric charge. Output DC power. Energy flow path 2. Array junction box or combiner. Input energy cables or wires from solar photovoltaic array. Wires from solar panels are connected to input connector in array junction box. Energy passes through the array junction boxes to reach the charge controller at the same rating or voltage as that of the solar panel. Output DC power from array junction box. Energy flow path 3. Charge controller. Input DC power received from array junction box. Output DC power passed on to the battery bank as per voltage setting in the charge controller in order to supply the same voltage to the battery bank. Energy flow path 4. Battery bank. Input DC power received from charge controller. Output DC power as per the inverter input voltage. Energy flow path 5. Inverter. Input DC power supply received from battery bank. An inverter is a device that converts battery power DC into alternating current AC of 230 volts. Output AC power of 230 volts. Energy flow path 6. AC load. Input AC power supply received from inverter. This power is utilized for different AC loads such as lights, fans, and other electrical equipments. Output electrical equipment usage. Analyze level of energy at each point. Level of energy at each block. Energy block solar photovoltaic array. Level of energy maximum of 30 volts DC power is produced based on the intensity of sunlight. Energy block, array junction box or combiner. Level of energy. All 4 panels are connected in parallel in this box and output would be 30 volts. Energy block. Charge controller. Level of energy. The 30 volts energy received from array junction box and regulates the voltage to 20 volts DC as required by the battery bank. Energy block. Battery bank. Level of energy as received from the charge controller. Energy block. Inverter. Level of energy. 24 volts DC is converted to 230 volts AC as per the AC load rating. Describe the safety precautions to be taken while in the block. Block-wise safety precautions. At solar photovoltaic array, connections to be made correct polarity and avoid loose contact. At different places placed solar photovoltaic panel, connections are connected at array junction box with suitable wire, color code, polarity and protective diodes. At charge controller, set the safest charging level voltage. At battery bank, check for proper polarities and the level of the solution to be maintained. At inverter, the battery bank output connecting cables with proper polarity are connected properly to avoid risk and hazards. Observe the DC and AC disconnects and apprise their importance. DC disconnects are observed between solar photovoltaic and array junction box, between array junction box and charge controller, between charge controller and battery bank, between inverter and battery bank. AC disconnects are observed between inverter and AC loads. Assuming the entire connection is ready for use, describe a sequence of switching on the off-grid solar photovoltaic electrical system. Sequence of switching on. Turn on the solar array DC main switch located next to the inverter. Turn on solar array junction box switch located in the switchboard and or next to the inverter. Turn on the main DC battery isolator. Confirm inverter is on and functions normally. Connect the AC loads step by step. Interconnect different blocks of an off-grid solar photovoltaic electrical system. Follow the wiring diagram as shown in the figure. Keep all the miniature circuit breakers and disconnects in off position. Sequentially, connect the different blocks. Wire the charge controller. Connect battery bank to charge controller or inverter through DC disconnect. Connect solar array output from combiner box through DC disconnect to charge controller. Connect charge controller output through DC disconnect to the input of the inverter. Connect the AC mains to the inverter. Connect the AC loads to the inverter output. Observations. Given below are the observations. Test the performance of the 1 kilowatt solar photovoltaic off-grid system. Switch on DC disconnect between combiner box and charge controller. Measure and record the solar array output reaching the input of array junction box. Switch on the DC disconnect between battery bank and charge controller or inverter. Measure the input to the charge controller or inverter from battery bank and record the observations. Switch on the AC mains disconnect to the input of the inverter. Measure input AC to the inverter. Switch on the inverter and observe normal functioning. Measure the output AC and record the observation. Connect the AC loads and measure load current and watts. Test the performance of 1 kilowatt solar photovoltaic off-grid system. Observations. Given below are the recorded observations. Sample calculation. Recap. In this session, we have learnt how to connect 1 kilowatt solar photovoltaic off-grid plant pre-installed, how to test 1 kilowatt solar photovoltaic off-grid plant. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you. A warm welcome to this session on Prepare Bill of Material for a 1 kilowatt solar photovoltaic installation. At the end of this session, you will be able to select components for 1 kilowatt solar photovoltaic after sizing. Draw a single line diagram for a 1 kilowatt solar photovoltaic system. Tools and equipments required. Inputs regarding sizing of photovoltaic plants. Inputs from market about component specifications. Input from market about cost of components. Discuss different possibilities of combinations of making 1 kilowatt solar photovoltaic installation. If the sanctioned load of a resistance is 1 kilowatt, then the total load shall not exceed 1000 watt at any time. If the residence uses full load for 1 hour, then the power consumption at this time is 1000 watt hour or 1 unit. As we are planning solar photovoltaic system which will generate maximum 1000 watt per hour, solar panels are available in 250 watt power. For 1 kilowatt solar photovoltaic system, we have to size the components. The components are inverter, battery bank, charge controller, solar array, solar structure. Other components: accessories, array junction box, disconnects, wires. For deciding on battery size or charge controller, etc., we have to decide on system voltage. System voltage is a DC value in volts selected as working voltage in an solar photovoltaic system. It also depends upon total capacity of the solar photovoltaic plant 1 kilowatt. Based on the capacity, the current rating of wires and cables in the system, disconnects, etc. will be determined for their specifications. Different possibilities of combinations of making 1 kilowatt solar photovoltaic installation are given below. 1 kilowatt solar plant single line diagram with parallel connected panels. 1 kilowatt solar plant single line diagram with series connected panels. 1 kilowatt solar plant single line diagram with series and parallel combination with battery. The cost of a solar system varies depending upon the size of the solar system, quality of the components used, and also several factors such as capacity, brand, and installation costs. Prepare a bill of materials for 1 kilowatt solar photovoltaic installation with parallel connected panels. The following bill of materials for 1 kilowatt solar plant single line diagram with parallel connected panels. When connecting solar panels together in parallel, the total output remains the same as it would be for a single panel, but the output current becomes the sum of the amperage, that is, current of each panel. Thus, the effect of parallel wiring is that the voltage stays the same while the ampere adds up. Parallel connection allows having more solar panels that produces energy without exceeding the operating voltage limits of inverter, which keeps charging capabilities steady. It requires thick wires to handle higher amperage, that is, current that will travel far away, about 10 to 15 feet from where the controller is situated. Bill of materials: solar photovoltaic channel, 250 watt power, maximum voltage Vm is equal to 30 volts. Im, maximum current is equal to 10 amperes. Open circuit voltage VOC 34 volts. Short circuit current ISC 8 amperes. 4 numbers. Solar inverter sample specification. Output AC 230 volts 50 Hz. Power rating 1.5 kilovolts ampere. DC input 20 volts to 60 volts. 40 amperes maximum. Battery input 24 volts. 1 number. Solar batteries 12 volts 100 ampere hour. 4 numbers. Charge controller 24 volts 20 amperes. 1 number. Array junction box IP65 1 number. AC main junction box IP65 1 number. Suitable connecting wires with disconnectors as required. Prepare bill of materials for 1 kilowatt solar photovoltaic off-grid plant with series connection of solar panels. Connecting panels in series will increase the voltage level and keep the amperage, that is, current, the same. The reason why series connections are utilized with controllers is that controllers actually able to accept higher voltages input and still be able to charge 12 volts or more batteries. It also depends upon specific situation. The disadvantage with the series wiring is that all panels are basically depends upon each other. If one parallel shaded, the whole string will be less efficient or at the same time not generating any power at all. An open in any one of the device will also interrupt current flow to all the remaining devices. Changing the resistance value of one device will change the current voltage and power values of all remaining devices. Prepare a bill of materials for the single line diagram. Observation. Bill of materials. Solar photovoltaic channel. 250 watt power. Maximum voltage Vm is equal to 30 volts. Maximum current Im is equal to 10 amperes. Open circuit voltage VOC is equal to 34 volts. Short circuit current ISC is equal to 8 amperes. 4 numbers. Solar inverter sample specification. Output AC 230 volts 50 Hz. Power rating 1.5 kilovolts ampere. DC input 20 volts to 60 volts 40 ampere maximum. Battery input 24 volts 1 number. Solar battery bank 12 volts 100 ampere hour 4 numbers. Charge controller type MPPT 24 volts 20 amperes 1 number. Array junction box IP65 1 number. AC main junction box IP65 1 number. Suitable connecting wires with connectors as required. Recap. In this session, we have learned how to select components for 1 kilowatt solar photovoltaic after sizing, how to draw a single line diagram for 1 kilowatt solar photovoltaic system. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you. A warm welcome to this session on estimate cost of a 1 kilowatt solar photovoltaic installation and prepare a quotation. At the end of this session, you will be able to select components and prices in market for a 1 kilowatt solar photovoltaic after sizing and prepare an estimate. Approximate cost of the project. Tools and equipments required. Bill of materials including electrical, electronic equipment and materials, mechanical fittings and accessories, civil equipment and materials, etc. and their cost. Cost of tools and consumables including rentals of installation equipment and logistics. Cost of mounting structures. Market trend on labor cost. Prepare a complete financial projection for a 1 kilowatt solar photovoltaic off-grid plant. Analyze all the possibilities of financial commitments. Prepare separate heads of expenditure for own and outsourced avenues. Prepare complete project report. Submit to experts and get evaluated the project. Record all through activities in observation. Project report of 1 kilowatt solar photovoltaic off-grid plant. Feasibility details of the project for 1 kilowatt power solar system as follows. Connected load 1 kilowatt. Energy consumption per month 1200 kilowatt. Tariff charged by Discom ₹6 per unit. Solar capacity suggested 1 kilowatt. Subsidy eligibility yes or no. USC number. Technical feasibility. System proposed and simple playback period. 1 kilowatt power solar off-grid system generates 20 to 25 units kilowatt hour per day. Average yearly generation. Expected generation per month 360 kilowatt hour to 400 kilowatt hour. Amount of savings on a monthly basis at 4 rupees 1500. Minimum units generated per day during cloudy days at 2.5 units per kilowatt, 5 units. Maxi units generated per day during sunny perfect day at 6 units per kilowatt, 15 kilowatt hour. Average units generated per day during average sunny day at 4.5 per kilowatt, 10 kilowatt hour. Load details can support a total nominal load of 1 kilowatt. Number of hours. Solar system generates power for 6 hours. Location and installation. Space availability for 1 kilowatt power system. 110 square meters of shadow-free area. Model of operation. Solar, off-grid. Mounting structure. Hot, dip galvanized steel. Prepare a complete financial projection for a 1 kilowatt solar photovoltaic off-grid plant. Quotation for design, supply, installation and commissioning of solar photovoltaic power plant of capacity of 1 kilowatt power with following specifications. Solar panel 250 watt power, 4 numbers. Cost per unit rupees 8,630. Total rupees 34,520. Solar inverter 1 number. Cost per unit rupees 9,650. Total rupees 9,650. Solar battery 12 volts 100 ampere hour, 4 numbers. Cost per unit rupees 7,800. Total rupees 31,200. DC ground fault interrupter 1 number. Cost per unit rupees 300. Total rupees 300. DC isolator 1 number. Cost per unit rupees 300. Total rupees 300. Charge controller 1 number. Cost per unit rupees 1200. Total rupees 1200. Mains AC isolator 1 number. Cost per unit rupees 400. Total rupees 400. Distribution panel 1 number. Cost per unit rupees 200. Total rupees 200. Interconnecting cables with connectors as required. Cost per unit rupees 1500. Total rupees 1500. Civil work for installation of solar photovoltaic units as required. Cost per unit rupees 15,000. Total rupees 15,000. Electrical wiring external as required. Cost per unit rupees 3,000. Total rupees 3,000. DC distribution units 1 number. Cost per unit rupees 450. Total rupees 450. Spares and tools as required. Cost per unit rupees 2,000. Total rupees 2,000. Miscellaneous electrical pipes, lugs, insulation tapes and clamps as required. Cost per unit rupees 1,600. Total rupees 1,600. Mechanical fittings, nuts and bolts, clamps, solar photovoltaic fixing frames as required. Cost per unit rupees 6,050. Total rupees 6,050. Mounting, erection and insulation inclusive. Maintenance inclusive. User training. Grand total 1,04,670 rupees. GST amount at 12.5%. Rupees 13,083.75. Subsidiary amount at 8.5%. Rupees 8,896.95. 1,04,670 plus 13,083.75 is equal to rupees 17,753.75. Subsidiary amount deduction 1,17,753.75 minus 8,896.95. Total amount paid by the customer rupees 1,08,856.8. Note: all components are IEC certified and MNRE certified products. Recap. In this session, we have learnt how to select components and prices in market for 1 kilowatt solar photovoltaic after sizing and prepare an estimate. Approximate cost of the project. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you. A warm welcome to this session on carry out visual inspection of photovoltaic modules. At the end of this session, you will be able to perform visual inspection photovoltaic modules before installation and in installed plant.
Information of different manufacturers or international standards. The International Electrotechnical Commission (IEC) has established quality standard certifications that are widely recognized throughout the solar industry and has gained acceptance in the past 15 years. IEC 61215. The IEC 61215 certifications is for crystalline photovoltaic modules. It covers the parameters which are responsible for the aging of photovoltaic modules. This includes forces of nature like sunlight including ultraviolet, UV, climate, changing of climate, coldness, warmth, humidity, mechanical load, hail, wind suction, wind pressure, snow. IEC 61646. The IEC 61646 certification is for thin film photovoltaic modules. It is in many aspects identical to the international standards IEC 61215 for crystalline modules. Additional tests take into consideration the degradation behavior of amorphous silicon due to the temperature and the irradiance exposure. Passing qualification tests means the product has met a specific set of requirements. Knowledge of possible failures. Failure clarification. For clarity purpose, it is important to be clear about what is considered a failure. Like any physical product, solar module issues could be classified in 3 categories. 1. Infant failure. Up to 2 years after delivery. Infant mortality failures occur in the beginning of the working life of photovoltaic module. From experience gathered, failures observed are junction box failure, glass breakage, defective cell interconnect, loose frame, and delamination. Number 2. Midlife failure. Up to 11 to 12 years of operation. An average of 2% of the photovoltaic modules is predicted to fail after approximately 11 to 12 years of operation. Examples of issues include junction box and cables failures, burn marks on cells, and encapsulant failures. Number 3. Wear out failure. From 13 years of operation. Wear out failures occur at the end of the working lifetime of photovoltaic modules. Failures encountered here are delamination, cell part isolation due to cell cracks, and discoloring of the laminate. Prepare a visual inspection checklist for the evaluation of mounted photovoltaic modules. Photovoltaic system performance is generally dependent on incident irradiance in the plane of the solar panels, the temperature of the solar cells, the spectrum of the incident light. Furthermore, it is dependent upon the inverter, which typically sets the operating voltage of the system. In the table given below, let us study the visual inspection for the evaluation of mounted photovoltaic modules. Failure or degradation of EVA encapsulant delamination. Possible causes are humidity plus moisture, UV sensitivity of adhesives, defective adhesion during manufacturing, external agents contamination. Effects could be moisture ingress, corrosion, transmittance losses, power losses, abnormal temperature distributions, failure or degradation of hot spots. Possible causes are different thermal expansion coefficients between cell components, shading, soiling, defective cells, cracks, fractures, low shunt resistance, faulty bypass diode. Effects could be burns, lower total current, damages on EVA or glass, encapsulant discoloration, power loss, thermal stress among cells, failure or degradation of soiling, glass discoloration, weathering. Possible causes are poor tilting of modules, defective cleaning protocols, long-term exposure in dusty environments. Effects could be transient or permanent transmittance losses, power losses, cosmetic changes, permanent allocation of particles over the modules, failure or degradation, faulty soldering, fractured cell. Possible causes are defective fabrication, transport and or handling, long-term thermal stress. Effects could be loss of generation or evacuation of charge carriers, uneven temperature distribution, increased series resistance. Define inspection checklists and prepare forms for filed inspections. Analyze the collected data, divide into various sections and document each section by the appearance or properties. Site information. Inspection at the back side of the module. Module data. Rear side glass. Back sheet polymer. Wires. Connectors. Junction box. Frame grounding. Define inspection checklists and prepare forms for filed inspections. Analyze the collected data, divide into various sections and document each section by the appearance or properties. Inspection at the front side of the module. Frame, frameless aired seal, glass or polymer, front, encapsulant front, metallization, silicon cell. Prepare a visual inspection checklist for the evaluation of mounted photovoltaic modules. Facilitate the user by easy questionnaire and answerable checkboxes like the one given below for the inspection of mounted photovoltaic module. The main components for evaluation are 1. Label, 2. Backsheet, 3. Junction box, 4. Wiring, 5. Frame, 6. Front glass, 7. Encapsulation, 8. Cells, 9. Cell metallization, 10. Cell interconnection. Component, label, possible defect, missing, poorly attached, information is missing, incorrect spelling. Component, backsheet, possible defect, delamination. Component, junction box, possible defect, faulty electrical connection, cracks or breaks or gaps in housing, sealant failure, electrical polarity not indicated. Component, wiring, possible defect, wire or wires missing or poorly attached, too short and or too thin. Component, frame, possible defect, damaged, adhesive or sealant failure. Component, front glass, possible defect, cracking, scratches. Component, encapsulation, Possible defect: delamination. Component: cells. Possible defect: fake, dummy pieces disguising missing material, cracks, partially covered, scratches, differently sized, edge chips, all cells very shiny. Component: cell metallization. Possible defects: fingers not connected to busbar, not the same pattern on all cells, fingers off edge of corner of cells. Component: cell interconnection. Possible defect: interconnection is discontinuous, cells connected in parallel or counterfeit, poorly aligned and or soldered. Cells connected in parallel or real cells. Defects are present, suggesting module is used rather than new. Summary: indicate if any defects and safety issues are present and some score.
Recap. In this session, we have learned how to perform visual inspection photovoltaic modules before installation and in installed plant. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you. A warm welcome to this session on practice to undertake precautions against module breakage. At the end of this session, you will be able to handle the solar photovoltaic modules safely in installation sites.
Tools and equipments required. Operation and maintenance manual for solar photovoltaic installation. Material handling equipment, ropes, lifting trolley, personal protection equipment kits. Practice the precautionary measures for safe working with solar modules. Every worksite presents different risks. No two worksites are the same. Before the solar installation begins, it is essential for the installer to visit the site, identify the safety risks and develop specific plans for addressing them. The guidelines for best practice in solar photovoltaic installation is given below. Solar photovoltaic roof mounting structure. Choose the right type of mount. There are 3 types of mounts: pole, roof ground and flush mounts, each of which can be installed in specific location. Aluminium frames to be avoided in coastal areas. Solar panels. Panels installed in high dust geographies like Rajasthan and Gujarat must have the solar panels tested with relevant dust standards. Take care of any sunlight obstacles before starting solar photovoltaic installation. Remove any unneeded obstacles such as branches that may be blocking sunlight to the solar unit. All 4 mounting clamps must be fixed properly for every solar panels. Proper care must be taken while lifting the solar panels at the time of mounting on the rooftops during installation. Handle the solar panels with care to avoid any damage to the panels. Fuse. The fuse shall have drain rail mountable fuse holders and shall be housed in thermoplastic IP65 enclosures with transparent covers. Cables. For the DC cabling, XLPE or XLPO insulated and sheathed. UV stabilized single core flexible copper cable shall be used. Multi-core cables shall not be used. For the AC cabling, PVC or XLPE insulated and PVC sheathed. Single or multi-core flexible copper cable shall be used. Outdoor AC cables shall have a UV stabilized outer sheath. Cables and wires used for interconnection of solar photovoltaic modules shall be provided with solar photovoltaic connectors and couplers. All cables and conduit pipes shall be clamped to the rooftop, walls and ceilings with thermoplastic clamps at intervals not exceeding 50 centimeters. The minimum DC cable size shall be 4.0 square mm copper. The minimum AC cable size shall be 4.0 square mm copper. In three-phases system, the size of the neutral wire size shall be equal to the size of the phase wires. The total voltage drop on the cable segments from the solar photovoltaic modules to the solar grid inverter shall not exceed 2.0%. The total voltage drop on the cable segment from the solar grid inverter to the building distribution board shall not exceed 2.0%. The DC cables from the solar photovoltaic module array shall run through a UV stabilized PVC conduit pipe of adequate diameter with a minimum wall thickness of 1.5 mm. Practice the precautionary measures for safe working with solar modules. Instructions for the team to follow in the site. Plans include equipments to be used for safe lifting and handling of solar panels, type and size of ladders and scaffolding if needed, fall protection for rooftop work, personal protective equipment for each installer. All equipment needed for the job should be inspected and verified to be in good working order before being brought to the work site. Lifting and handling solar panels. Ladder safety. Solar construction often involves working on roofs and form ladders. Choosing the right ladder and using it properly are essential. Check if all panels are easily accessible for cleaning. Check if all panels are properly installed to withstand heavy wind load. Check if paint of frames in good condition. Check for carpentry and electrical trade related injury. Check for risk of traditional roofing. Check for potential for faults of many stored rooftops. Lifting and arranging unwieldy solar panels.
Recap. In this session, we have learnt how to handle solar photovoltaic modules safely in installation sites. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you. A warm welcome to this session on Demonstrate Hotspot on modules through audio-visual aids. At the end of this session, you will be able to troubleshoot a solar plant reported to generate much lesser than installed capacity by taking thermal image of the array. Interpret the findings from thermal image with defects of the solar panel and take remedial actions.
Tools and equipments required. Thermal camera, laptop or desktop. Visit to a larger solar photovoltaic plant. Digital thermal camera. A digital thermal camera is a device that creates an image using infrared radiation, similar to a normal camera that forms an image using visible light. Instead of 400 to 700 nanometer range of the visible light camera, infrared cameras are sensitive to wavelengths from about 1000 nanometer to about 14,000 nanometer. The practice of capturing and analyzing the data is called thermography. Thermography is the method used to measure hot spots based on lock-in and time-resolved techniques. Using this technique, hot spots may be conclusively identified before or during field installation with iris inspection. The technique works in ambient light and directly measures the local heating due to defects. Verify the performance of thermal camera. Study thoroughly about the digital thermal imager or camera for its utility, handling and methods of fault finding in field. Carry the thermal camera in the early morning or in the evening. Visit the solar photovoltaic plant. Capture the pictures of solar panels in operation, morning, afternoon and evening. Capture pictures of the solar panels in operation. The red spots indicate modules are consistently hotter than the rest, indicating faulty connections. The hot spot within one solar cell indicates physical damage within the cell. This thermal image shows an example of patchwork pattern which indicates that this panel has a defective bypass diode. This thermal image shows larger areas with elevated temperatures. Thermal image of backside of solar module taken. Its corresponding visual image is shown on the right. Transfer images to the computer and tag them. The images from the thermal digital camera are transferred to the computer to analyze the thermal image patterns through respective software, analyze defective modules and tabulate probable reasons. Error type: manufacturing defect. Example: impurities and gas pockets. Cracks in cells. Incomplete edge isolation. Crystalline defects intersecting junction. Overfiring, PN junction, punch through. Scribe line shunts. Incomplete removal or redeposition. Metal practices and bridges on backside. Print alignment errors. Module manufacture. High resistance or cold solder points. Current mismatch between cells. Appears in the thermal image as a hot spot or cold spot. Error type: damage. Example: cracks. Cracks in cells, a warmer part of cell. Appears in the thermal image as cell heating, form mainly elongated. Error type: temporary shadowing. Example: pollution, bird droppings, humidity, one cell clearly warmer than others. A pointed heating. Appears in the thermal image as hot spots, delaminated cell. Error type: faulty interconnections. Example: module or string of modules not connected. An entire module warmer than others. Appears in the thermal image as a module or string of modules is consistently hotter. Suggest remedies for defective panels. To keep the solar panels active for longer time, it is important to make regular cleaning of them and check their connections. The system must be inspected by a professional on a yearly basis. To prevent panel damage, it must be made sure that the panels are located in place that is protected from severe weather conditions. To prevent hot spots, it must be made sure that the system is inspected regularly and the connections are kept tight. Also, the panel's display panel must be watched for any error messages that may indicate a problem. To prevent PID, that is potential induced degradation, the panels must be protected from extreme temperatures. To prevent from soiling, snow or bird droppings, regular cleaning of solar panels must be done. Finally, the efficiency of the solar panels can be improved by ensuring the installation of the panels in a location with full sun exposure.
Recap. In this session, we have learnt how to troubleshoot a solar plant reported to generate much lesser than installed capacity by taking thermal image of the array. How to interpret the findings from the thermal image with defects of the solar panel and take remedial actions. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you. A warm welcome to this session on Mark locations for components of solar photovoltaic electrical system on site. At the end of this session, you will be able to sketch a layout for fixing various components of solar photovoltaic system on site.
Tools and equipments required: 50 to 100 feet measuring tape, digital camera, record or logbook or diary, product manual for PCU or inverter, battery, etc. along with their dimensions, mounting angles, bolts and nuts. Plan exactly for locating the various components. Planning for locating various components needs a well-conducted assessment of the roof and also requires answers to the following questions. Is the roof suitable for installation of solar photovoltaic? Is the solar resource high enough? How much installed capacity could be fit on the roof? How much energy could the system deliver? A rooftop solar photovoltaic installation comprises of photovoltaic panels assembled in arrays, mounting frames to support the panels and secure them to the roof, wiring, inverters and other components depending on the type of installation. The roof site must be able to accommodate all of these components, which requires examining the following aspects. Accessibility. The roof must be accessible to carry out installation and maintenance. It must be possible to lift the solar system components onto the roof and for personnel to physically access the site to install and maintain the system. Roof configuration. A roof plan can help quantify the roof area available for the PV power plant. The plan should be indicate the location, height and slope of the roof itself as well as any additional structures present on the roof. Identify any possible conflicts in use of the roof such as helipad or communication antenna and contact relevant bodies to ascertain if any special permissions is required to use and alter use of the roof space. Roof materials and structure. For the existing buildings, first find out when the roof would need replacement. If a roof is nearing the end of its lifespan, it is more cost effective to install the rooftop photovoltaic system once the new roof is in place. It is also easier to integrate a system into the design of new roof. Aesthetics. Check that the solar photovoltaic module would not negatively affect the aesthetics of the building. From the street level, solar modules will be more visible on a sloped roof than on a flat roof. If they will be seen, find out if there are any local buildings restrictions preventing a visible rooftop solar photovoltaic installation. Roof leasing. If planning to lease the roof space to the owner of the rooftop photovoltaic system, consult a legal advisor who would be able to confirm whether that the type of arrangement is permissible. Electrical load. Obtain the current and expected electrical load of the building or facility. Should the load be comparable to or less than the electricity generated through solar photovoltaic, plan a smaller system or plan to use the excess energy, either store the energy in batteries, send it to another building within the facility or feed it into the grid. Component dimensions and installation requirements suggested by manufacturers and hint about moving components to required places. Roughly 110 square feet or 10 square meter area is required for a 1 kilowatt installation. Accordingly, assess the site and recommend for more capacity. This will benefit the business as well as customer. Remember, inverter should be located in a room or shelter protected from sun and rain. Batteries should be kept in a room or shelter in a rack and the room should be ventilated. If such space does not exist, suggest the customer to possibility of constructing shelters for equipments. For cable routing, do keep in mind that the inverter should be kept as close as possible to the DC combiner box as DC side wire loose increases drastically with the length of the wire. Draw a rough sketch of how the cables will be routed and estimate the length of the wiring that may be required up to the switchboard. Sketch out a drawing to show locations of all components in the site. Light. The sun gives off light even on the cloudy days. Panels. PV cells on the panels turn the light into DC electricity. Inverter. The current flows into an inverter which converts it to AC electricity ready to use. The electricity. The current is fed through a meter and then into the consumer unit. Power supply to the house. plug and switch on, the electricity that has been generated is ready for use. The grid. Any electricity that is not consumed is exported to the grid for others to use.
Recap. In this session, we have learnt how to sketch a layout for fixing various components of solar photovoltaic system on site. Hope you have understood all the concepts in this session. See you in the next session with a new concept. Thank you.
Today I am here to discuss about the effect of seismic load on a structure. Before starting our discussion, I would like to discuss about the various loads which may occur on any structure. First one is dead load. Dead loads are the majorly